Hi, everybody. Welcome back. This is a very brief introduction to differential equations. So the truth is they include this material in Calculus 1 and a tiny bit more in Calculus 2, truthfully as an excuse to just make you do more integrals. But um, it's probably worth taking this opportunity to give you an introduction to what a differential equation is and show you, how to solve some very simple ones. Whereas many of you will take a whole class in solving differential equations using lots of different tricks, things that you'll learn more about in Calculus 2 and some stuff in Calculus 3 that you'll need before you dive into those. But a differential equation, just an equation with a derivative in it. So here's a really simple example, right? So this equation says dy dx, that's dy over dx, that's my derivative, is equal to something, 3x cubed plus 5. Here's another one. This doesn't have x's and y's as the variables. It's got p's and t's as the variable. This is the kind of thing you might see, maybe where p is price over time and you're doing some sort of an economics class. It says the derivative of p with respect to t is equal to some constant k in this case times p squared. Right? Here's a more complicated one. Right? This is a second order differential equation because it has a second derivative in it. Right? And it's this long complicated connection between the derivative of x with respect to t and the second derivative of x with respect to t, and also how that connects to x and sine of t and all sorts of stuff. Solving something like that is awful, right? I mean, that's a much more complicated kind of question. And it's the sort of thing you'll run across when you take a whole class in differential equations. So, okay, one of the most important things to remember, though, is unlike the sort of equations you saw in algebra, where the solution to an equation was a number, or maybe a couple of numbers, the solution to a differential equation is going to be a function, because the equation is all about the derivative of some function that, so it does something, it satisfies this equation. So for example, this equation says that the derivative of y with respect to x is 3x squared. Okay, so if you think about that for a second, it's kind of obvious what the solution should be. What should y be? What's a function that when you take its derivative, you get 3x squared? Well, I mean, obviously it's got to be x cubed, right? We just know this because we know how derivatives work. You could say, okay, what I'm going to do is I'm just going to integrate this and get 3x squared, right? If you think about this in terms of integration, then maybe something else tips off to you, because if you think about that, say x cubed minus 2, oh, that's also a solution, because when I take the derivative, I'll get 3x squared, and the derivative of the minus 2 there will be 0. So that goes away. So we need a plus c, right? And that's what the general solution to a differential equation is. It's all the different solutions to that equation. And so we would say the general solution here is x cubed plus the c, because we might have a c there, that when we take the derivative we don't notice. So any number that we add to the end of x cubed, would still give us another solution. Then might have a problem like this, right, where we want to actually figure out what that c is for a particular problem, where we know a little bit of extra information. So in this case, we know that dy over dx is 3x squared, right? Same equation, but now I want the solution that goes through the point 1 comma 5. So I need a solution that goes through a particular point. So that'll be a particular solution. In other words, it won't have a plus c in it. We'll be able to figure out what the c is. And in this case, simple enough, right? Our general solution should be x cubed plus our c. But then we can figure out what c is, because we know that we want the solution that goes through the point 1, 5. That means that when x is equal to 1, y should be 5. So I can plug 1 in there for x and 5 in there for y, do a little bit of algebra, and get that c has to be 4. So this is a particular solution, x cubed plus 4, because they gave us some more information and we were able to narrow ourselves down from having infinitely many solutions where any number c would give us a solution to this one particular one. Oh, here's a slightly more complicated one. So this is an example of something called a variable separable differential equation, because if you look at this, I could do a little, well, it looks like algebra, right? To take all the x's to one side and all the y's to one side. So let me show what I mean. If I were to have a function that looks like this, right, where there's a dy over dx is equal to some function of x over some function of y, then I just do a little algebra, right? I take the denominator and move it to one side, take the numerator and move it to the other side, and notice that the way this is rigged up, that gets all the x's on one side and all the y's on one side. And then, of course, I just integrate both sides, and there we go. So let's see how this works with this example. So I need to multiply through by the y squared. That'll move the y squared over with the dy, and then multiply through by dx, and that moves the dx over with the 2x plus 3. Now notice that all the y's are on one side, all the x's are on one side, just like we normally do when we solve an equation. We want to move all the x's to one side, all the y's to one side. Now we can just integrate both sides. Okay? And when you do that, okay, this becomes really easy, and of course gives away part of the reason why they put these kind of questions into Calculus 1 classes, is it's just an excuse to make you do more integrals. So now how do you integrate y squared? You get y cubed over 3 plus some constant. And then how you integrate 2x plus 3? It'll be x squared plus 3x plus presumably a different constant. Okay, so how could we deal with this? Well, remember those constants are just placeholders for numbers that we don't know. So I really could just move all the constants to one side and call it just one constant. Because again, it's really just a placeholder for a mysterious number that we don't know. So I would have like y cubed over 3 is equal to x squared plus 3x plus c. And maybe better, I could take the 3 to the other side, you know, and then just have y cubed by itself. All right, let's try another one. So this is written in differential notation. So x squared dy is equal to secant y dx. So it's the same idea. I just move all the x's to one side and all the y's to one side. So what I need to do is, I don't want to divide by the dy because I'm about to do an integral. So what I'll do is I will divide by the x squared and divide by the secant of y. In other words, I'll take the secant y over there with the dy and the x squared over with the dx, but leave the dy and the dx in the numerator because that's obviously where they're going to have to go if I'm going to integrate. And now you go, okay, how do I integrate both sides? Well, let's do a little bit of algebra. How am I going to integrate 1 over secant y? Well, if you think about secant, maybe you remember, wait a minute, what is secant? It's 1 over cosine. So all I have to do is turn the secant y in the denominator into 1 over cosine, and that actually becomes a lot easier to deal with. Instead of a secant y in the denominator, just a little bit of trig identity turns that into a cosine of y. Now it's up in the numerator. And how am I going to integrate an x squared in the denominator? Well, first step is to turn that into, x raised to a power. And so instead of making that x squared in the denominator, I make it x to the negative 2 times my dx. Now you integrate both sides, and when you integrate cosine of y, you get sine of y. And when you integrate x to the negative 2, you get x to the negative 1 divided by negative 1. Now, one mistake that's easy to make here is you see that x squared in the denominator, you might think, oh, I'll make that log of x squared. But remember, that doesn't work that way, right? That only works if it's 1 over x, right, that we're integrating. This is an x squared, so we have to make it x to a power and use the power rule. Okay, so now let's put the c's together and make it super easy to see what's going on, because again, those c's are just placeholders for constants we don't know. So we can combine them all into one constant that we don't know. There we go. Here's one more. So this is an interesting example because it's something you would have seen before, in maybe high school science classes or physics or something. So this equation, let's stop for a second and look at what it says. It says the derivative of q with respect to t. So first off, that means our variables are q and t, right? We're looking for q as a function of t. And think of q as quantity here, okay? So the derivative of q with respect to t is equal to some number times q. Okay? So in other words, I take the derivative of a function and I get the function back again, maybe multiplied by some constant. And if you think about it for a second, you can probably make a guess at what kind of a function you would have if you took the derivative and you got the same function back, maybe with a constant in front of it. So we'll see if your guess was right in just a second. Right. So what does this say about the way that this quantity changes? Well, what it says is the rate of change of my quantity, right, the derivative, is equal to some multiple of the quantity itself. So this is the kind of thing that happens like when bacteria multiply, right? So what happens is your bacteria will split, right, every so often. So what happens is, what's the rate of change of your bacteria? Well, it's equal to the number of bacteria you have, because it's going to double every time, right? Every bacteria becomes two more. Okay? This sort of thing shows up in lots of biological and physical processes. So, all right, let's see how we would solve this. So let's take all the Q's to one side and all the T's to one side. And of course, K again is just a number. So it will just stick around in there. It's just a constant, like 3 or 7 or 2 or something. So if I take the Q over to the other side, then I get dQ over Q. And on the right-hand side, I'll have K, and I'll move the dt over there. And when I integrate that, of course, you get log of absolute value of Q from integrating the 1 over Q. And K is a constant, so when you integrate a constant, you get a constant times the variable we're integrating. So the variable here is T, so this will be KT. And we have two constants, but we could really just combine those and make them into another constant. And I'm going to call that C3, not just C, because I want to do a little bit more algebra still. I want to go ahead and solve this thing for Q, so you can see that this actually is something you've seen before. How would you solve for Q? Well, the way you undo a log is with an exponential function. So imagine that I'm going to e both sides. That would say that Q is e raised to the kt plus whatever this constant is power. And that's awesome, right? Then we've got a nice formula for Q. Q is e to the kt possibly plus some constant. But now if you think about that for a second, that doesn't look maybe like something you've seen before from physics, but with a tiny bit of algebra I can make it look like that, because e to the kt plus a constant, well, I've got things being added in the exponent. So I could turn that into two exponentials that are being multiplied together, right? That's e to the kt times e to the c3. And maybe what I can do is just call that, okay, so why did the c suddenly come in? Well, remember, c3 was just a constant, I don't know what it is. So e to the c3 is still just a constant that I don't know what it is. So I can just replace that with another c standing for some constant, and I don't know what it is. Okay. Well, the way you probably have seen this in science books and so forth is not with a C there, but with something like a Q0 there. Remember, like a physics class, Q0, that would be the value of Q, the quantity that's there when time is 0. And so what that would mean is, if you plug in 0, right, I get e to the 0 times my constant. If I call that, right, my Q0, because of course e to the 0 will just be 1. In other words, that constant there will very often show up in a science book as written not as a constant, but as like Q0, the value of Q when t is 0. Okay. And if you've seen that before, maybe recognize what this looks like. This is usually called exponential growth, or maybe exponential decay. In a physics book, you may see this in the decay, like for the half-life of some radioactive material or so forth, or in a biological context, they're doing some sort of exponential growth. Okay. So again, you'll see this sort of thing again in other classes. Physics and chemistry and biology use this same idea, because this idea of something that grows at a rate that's proportional to the quantity you already have shows up all over the place.